Hello, my name is Dana. I'm an undergraduate research assistant at the Institute of Smart Systems and Artificial Intelligence. In this video, I'm presenting the summary of our paper titled TFW Annotated Thermal Faces in the Wild Dataset. Face detection and localization of facial landmarks are the primary steps in many face applications such as face recognition, emotion recognition, virtual makeup, age and gender classification, and drowsiness detection. Numerous benchmark datasets such as FDDB, MALF, wider face, and etc., and deep learning-based models such as TINA face, Retina face, MTCNN, YOLO5 face have been introduced to address face detection in the wild. However, variations in head pose, facial expression, occlusion, and especially illumination still pose challenges. Nowadays, thermal cameras are used to address the illumination problem. In addition, they are invariant to weather conditions. Also, they allow to capture even distant images. Last but not least, thermal cameras gained popularity during the COVID-19 outbreak thanks to their ability to contactless measure temperature. However, thermal cameras have a few limitations, such as high price and inability to see through transparent materials. In this work, we address thermal face detection and facial landmarks prediction problems by presenting a thermal face dataset with annotated bounding boxes and facial landmarks. The existing thermal face datasets are summarized in Table 1. As we can see, most of the datasets were collected in controlled environments. Moreover, many of them were recorded using low-resolution cameras. Most importantly, only a few of them provide annotations for bounding boxes and facial landmarks. The datasets collected in the wild are not suitable for training face detection models due to the lack of annotations. In this regard, we present a new thermal face dataset that was collected in controlled, semi-controlled, and uncontrolled conditions. We used a FLIRT 540 professional thermal camera with a resolution of 464 by 348 pixels to collect the dataset. We manually annotated the dataset with bounding boxes and 5-point facial landmarks. In this work, our main contributions are as follows. Firstly, we present a novel thermal face dataset with annotated bounding boxes and facial landmarks. The dataset was collected in controlled, semi-controlled, and uncontrolled conditions to simulate real-world scenarios. Secondly, as a baseline, we trained the YOLO V5 object detection and YOLO5 face detection models on our dataset. In addition to our test set, we evaluated the models on an external thermal face dataset, RWTH Aachen, to show the efficacy of our dataset. Thirdly, we have made the dataset, annotations, source code, and pre-trained models publicly available at our GitHub page under the Creative Commons Attribution 4.0 International License to facilitate research in thermal face analysis. The controlled indoor set contains 5,112 thermal visual image pairs of 142 subjects. We constructed this dataset using our previously published Speaking Faces dataset, where subjects participated in 2 sessions that consisted of 2 experiments. In the first experiment, the participants sat silent and still, while the camera recorded them from 9 different positions. In the second experiment, subjects read a series of commands on a video screen and were recorded from the 9 positions. The semi-controlled indoor set contains 780 thermal visual image pairs of 9 subjects. We considered 4 real-world scenarios to collect this set. Subjects walking with and without face masks under good illumination, and subjects walking with and without face masks under a low illumination. In the beginning of each session, subjects were asked to do predefined actions such as turning their heads to the right and left, up and down, and after that they were allowed to walk in any direction by doing random gestures. We collected both thermal and visual images. The uncontrolled outdoor set provides 4,090 thermal images of 15 subjects. The dataset was collected during the summer in different locations on different days. In addition, we tried to collect the data in different weather conditions such as sunny and cloudy to provide some variability in temperature. Our main objective was to collect thermal images of a randomly walking crowd in public places. The participants walked in any direction inside the camera's field of view, making random gestures. In some cases, the participants were asked to wear facial masks. To manually annotate the dataset, we used the graphical annotation tool named LabelMe. The RGB thermal images are challenging for annotation because the contours of the eyes and lips are not fully visible. Therefore, we processed them to ease the manual annotation as shown in the figure below. In the beginning, we converted thermal images from RGB color scale to grayscale. Then, we inverted the grayscale images to get the negative ones. After that, we applied gamma correction to the negative images to increase the brightness. Finally, we inserted bounding boxes and facial landmarks on the enhanced images. The statistics of the annotated data are as follows. The controlled indoor set contains 5,112 images and the same number of labeled faces. All faces are in the large category because the heights of the bounding boxes are higher than 125 pixels. The semi-controlled indoor set has 780 images and 1,748 labeled faces. All faces are in the middle category. The uncontrolled outdoor set contains 4,090 images and 9,649 labeled faces. The faces were equally distributed between the small and medium categories. Overall, the dataset contains 9,982 images and 16,509 labeled faces. To validate the effectiveness of our dataset, we trained the YOLO v5 and YOLO 5 face models on our dataset. The YOLO v5 model was released in 2020. It is faster and more accurate than the previous YOLO models. It provides models of different sizes as nano, small, medium, and large. We trained the YOLO v5 as a general object detection model for a single class face. The YOLO 5 face is the adapted version of the YOLO v5 model. It has an additional regression output for 5 facial landmarks. It also provides models as nano, small, medium, and large. We trained the YOLO v5 without facial landmarks and YOLO 5 face with facial landmarks models to see whether using the facial landmarks as an additional supervision signal provides more accurate results. After training the models, we evaluated them on the test set of our TFW dataset and external RWTH-IHIN dataset. We used the average precision metric to evaluate the models, setting the intersection over union threshold to 0.5. In addition, we calculated normalized mean error to assess the performance of the YOLO 5 face models on predicting facial landmarks. The results are shown in Table 3. We can infer several conclusions from the results. Using the facial landmarks as an additional supervision signal provides more accurate results in detecting large faces. All models successfully detected all faces in the controlled indoor set. The most accurate result on the challenging outdoor dataset was obtained by the YOLO v5N model with 97.29%. The accurate results on the IHIN dataset illustrate the efficacy of our dataset as it was not used during the training and validation steps. The normalized mean error for the indoor and IHIN datasets are close because both datasets were acquired in controlled conditions and faces are large. However, the normalized mean error for the outdoor dataset are noticeably higher because the dataset is much more challenging than the indoor and IHIN dataset. We also compared our thermal face detection model with the visual face detection model under different conditions. For this objective, we used our semi-controlled indoor dataset. We tested our YOLO v5S face model on thermal images and the original YOLO 5 face model on the visual images. The results are as follows. In the first case, when the illumination was normal and subjects were without face masks, both models performed well, showing the high accuracy. In the second case, when subjects were with face masks, the accuracy of our thermal face detection model dropped to 84.07%, while the accuracy of the visual face detection model was still high. This can be explained by the limited amount of thermal images with face masks in our dataset. In the third case, when the illumination was low and subjects were without face masks, the accuracy of the visual face detection model dropped to 79.84%, while the accuracy of our model was still high, which is about 97.20%. This highlights that our thermal face detection model is illumination invariant because of the nature of thermal cameras. In the last case, the illumination was low and subjects were in face masks. The accuracy of the visual face detection model decreased further to 65.5%, while the accuracy of our model was 85.89%, similar to the case with normal illumination. This is a demo demonstrating the performance of our model on the uncontrolled outdoor environment. More details are provided in the paper and in our GitHub. Thank you for your attention.